In the last video, we learned how to find the area of some basic 2D shapes. We can use those concepts and build some basic volumes of 3D objects. You'll be surprised that there are only a few types of shapes, 3D shapes that we need to solve for the volume of over and over in engineering problems. Those are the sphere, a rectangle prism or a cube, a triangular prism, and a cone. And a lot of shapes, a lot of real physical systems can be assumed to be some form or combination of those. So understanding those volumes and remembering how to solve for them quickly is very useful. The easiest type of volume to solve for is one where we have a surface and we just extrude it. That's the same concept as when you were a kid, Play-Doh, and you have some kind of a star or a circle, and you push Play-Doh through that object, and you have now the same shape replicated all along a certain length. That's what we get when we have a cylinder. For a cylinder, we have a circle that we push across some length, L. So in this case, we know how to solve for the area of that circle, pi r squared. And if we want to find the volume, we multiply that area by the length L. We do this for any type of extruded surface. Find the surface area, which we also call the cross-sectional area, and we'll talk about that more in a future video, and we just extrude it across here, right? So we just multiply by length L. So the area has an r squared or a meter squared, inches squared type of unit. The volume has r squared times L, so it's the length, the unit length cubed. So this would be inches cubed, cubic meters, cubic centimeters, things like that, right? So make sure you understand the difference in your units between an area, which would be something squared, and a volume, something cubed, right? The r squared and the length L. So it'll be a length scale cubed. All right, what other extruded surfaces do we have? We have rectangular prisms. If we look at the surface or the cross-sectional area as this blue surface, we can find that area as the height multiplied by the width, and we extrude it by some length L. So the volume of this would be the area HW times L. You can also look at it as the area is this top surface, right? W times L, and you extrude it by H, you get the same exact volume. If we looked at it from a perspective of a cube, all three of these lengths would be the same, right? The height, width, and length are all L lengths. So this would just be L cubed. And finally, we have a triangle that's extruded across by some length L. We know how to solve for the area of a triangle. The area of it is 1/2 this height, right? We're assuming from here to this base here, and this is the length of the base. So 1/2 the height times base is the area, so the volume will be that times the length, right? So when you have extruded volume, extruded objects, solve for the area of the surface and then multiply that by the length it is extruded. So a fairly straightforward process to solve for a bunch of complex extruded objects. We'll take a look now at some more complex systems where our volume is built not just through extrusion. So what other objects do we have where it's not just a surface that's extruded across? A sphere is a common one, right? We have a lot of objects that are rotating, a surface that's rotated across. So I'm going to tell you right now that the volume of the sphere is 4/3 pi r cubed. This equation shows up over and over. I'm going to show you the derivation, or one way to derive it. It's not something that you will want to memorize the derivation. Memorizing this equation is useful because it does come about over and over. So this is my radius r. The way we can think about it is I can integrate. So if you haven't looked at integration methods, I'll put in a link to the playlist in the description below. But if you're just learning geometry right now, you probably aren't learning integration. So you could just memorize this. But for those of you who are revisiting geometry, maybe you've taken calculus already, I'll walk through the derivation, which you probably have seen. So the first thing we need to do is describe the equation for half of the sphere, just the line that represents this. So we're going to look at the origin, my x equals 0, y equals 0 point at the center of the sphere, and we'll look at one of that center planes, right? So this will be considered negative r for my x. This will be considered positive r for my x. And this we can describe as x squared plus y squared. And we know that it will equal to r squared. When I want to use integration, I can solve for the incremental volume term here and integrate across either the x or y direction. I'm going to integrate across the x direction. So dv, this incremental volume space here, is equal to pi y squared, because y is this height right here, which is like the radius of this disk, which you can look at as a cylinder. So the area of this top surface of this cylinder is pi r squared, but r is not the same as this r. It's the y value, right? It's the radius of here, which is changing as you move along the x direction, times the length component, right? That's what we looked at and talked about in the cylinder. Well, that'll be this small sliver, that thickness is your dx term, right? So we can just integrate this and apply the y value that we get here. So what will that be? That will be the volume, the total volume is integral of this. So pi y squared, if I rewrite this, this will be y squared is equal to r squared minus x squared, or y is equal to square root r squared minus x squared, sorry, square that, times dx. So now I can just take this integral with respect to x. So yeah, I guess I could have skipped that step. So pi times y squared dx. That's what this is here. This is your dv term, right? And we're going to go integrate this from negative r to r. That represents from negative r, and we integrate all the way across here to positive r. So this disk is changing in the y value as you move along here, dictated by this red surface here, which we have as the y or y squared equation here. All right, so this is with respect to x, not with respect to r, so this is basically seen as a constant. So we get pi times the constant r squared times x, right, minus the integral of x squared is x cubed over 3. Then we apply our lower and upper limits, negative r and positive r. There's my upper limit, there's my lower limit, and then we get that 4/3 pi r cubed. I'm going through this rather quickly because I have a separate video where we can revisit this in the integral playlist. But just to show you that this is true. Now, would I recommend memorizing this integration process? No, I would memorize, if I were you, what the actual volume is, but it's important to know where it actually comes from. So we're going to do something similar here for a cone. So here we have a cone, right? So the base is a circle with a radius r, and then it shrinks up until a single point up here. And we say this height h is from this point here down to some perpendicular, once it's perpendicular to the base, right? So from a point here, the shortest line that you can draw here, that's what we define as our height h. Now, if I want to prove out that this is true, we can integrate just like we did for the sphere. The concept is very, very similar. In this case, we'll say, let's define the origin, my 0, y, and 0, x point, as the point up here. So down, going this way, y would be equal to negative h down here. And so I can define my linear equation for this y edge right here. Sorry, yeah, so this edge right here. Y would equal, if this was my origin, y is coming down as negative, x is positive in this direction here. The slope would be negative h over r, right? Rise over run, it's dropping by h, so negative h. Run will be r. right? So that's my slope times x plus the y-intercept. The y-intercept will be 0 because I'm defining this as my origin. Then dv, so I'm going to take my disk in this direction and move it up and down in the y direction, whereas I did for the sphere in the x direction. dv would be the area. This will be pi x squared instead of pi y squared. And now it's dy instead of dx because the thickness is in the y direction. And then we can integrate it just like we did for this case up here. So we got the pi y squared, or sorry, x squared, right? X squared right here. So y r minus over minus h. That's my x term right there. So this is x squared dy. And what are my lower and upper limits? My lower limit will be down here, negative h. My upper limit will be up here at this origin, at this peak point, that would be 0. And so I just need to integrate this. So my only variable term is my y value, so I could pull everything else out. I'll pull out my h squared term, my r squared term, my pi term. This negative sign drops out because of the square component, and so I'm just integrating y squared essentially. So I integrate y squared, I get y cubed over 3, multiply by that constant up there, and then apply my upper and lower limits, and I get my 1/3 pi r squared h again, right there. Now, one thing to notice is when you have a triangle or a cone or anything shaped like this 1/3 or 2/3, depending on which direction you're looking at, comes up over and over. What this represents is if you look at a triangle and you're trying to find the center of mass of the cone, it's 1/3 of the way up here, right? If it was a rectangular prism, it'll be halfway. You see it's bottom heavy down here, so it does make sense that it'll be closer to the bottom than it would be at the top, and closer to the below the halfway point, right? So this 1/3 point shows up a lot. Another thing to notice is when we looked at the extrusion piece, we said we multiply this the base area by the extruded length. It's kind of like the concept of this h value, but because this base area is changing as you move up, we also had to add this 1/3 piece. So this is basically 1/3 times the base area, which is in this case a circle, so pi r squared, times h. Well, can we take this concept to other systems? And the answer is yes. So if I have a triangular pyramid, right? So I have a pyramid, looks like a cone, but the base is a right triangle. So let's define this as a right triangle. So let's say I have a right angle down here at this base triangle down, defined by, I guess you would call this a height W, which is the width of one of the widths of the triangular prism pyramid, and the length L will be like the base component, right? So if I follow the same logic, I can solve for the volume of this, assuming this is a right angle, as 1/3 times the area of this triangle, 1/2 W times L, times the height H, assuming that this height H is from this peak point down the closest contact point to this base triangle, which will make it a perpendicular line, or vertical line here, right? And this is true, right? This is the area component of this piece right here. It's a similar, you can use a similar method to integrate and solve for that. Similarly, we can have a rectangular prism, pyramid. I keep saying prism. Rectangular pyramid, right? So your base is a rectangle with W, length L. Your height, again, defined as your peak point here, dropping down to this base rectangle. Then we can define it as 1/3 times the base area, W times L, times the height H, right? With these basic concepts of volume, you can solve most of the things that you need to solve volume for most engineering problems, at least without using a computer modeling system. So understanding and memorizing these concepts, not the integration, but the concepts and the final value, will help you a lot. In the next set of videos, we'll take a look at surface areas and cross-section areas, which are basically looking at these volumes and finding the 2D components of these volumes, kind of taking the reverse of what we just did. Those are also very important for things like flux or properties that are dictated or influenced by the surface area, the cross-section area. It's important to understand how they relate, and because of that relationship, solving for them becomes very important.